Hello everybody. So today we are going to talk about coloring planar graphs and maps. So let's start with the following question, problem. Let's say that a cartographer wants to color a map, kind of political map with countries. So he wants to color the map by assigning colors to countries in such a way that no two countries are colored. No two countries that are colored the same way, the same color, share a boundary. So let's consider an example. Let's say I first use the yellow color, and I'll color some of the countries in yellow. Well, maybe I'll start, let's say, with this country. So I color it in yellow. Like that. Maybe I should not be so precise because it takes time. All right, this is yellow. Now I cannot color its neighbors in yellow, but I can color some of the further away countries in yellow. So say I can color this country in yellow. And then I can still color this one in yellow. All right, but I think that's it. So I cannot color any more countries in yellow. So let's use another color, say green. Which one do I want to color? Well, let's color this one, for example. So this one in green. Now, which one can I? So I still can color, say, this one in green as well. But that's it, so no more green. So I need to use another color. Let's say use blue next. So I can color, say, this country in blue. And then I can color this one in blue. And say this one also blue. But this last one left over there at the top right corner, I cannot color in blue, I cannot color it in green, and I cannot color it in yellow, so I'll have to use yet another color, say purple. So let's color it in purple. So this one is going to be purple. So now we got a nice map colored in such a way that no two countries that share a boundary are colored the same way. Now the question, now one can ask the following question: what is the minimal number of colors that would allow to color any map, that would work for any map. So, well, let's consider one more example over here. So here on this example, what we can see is that here we have 4 countries, and they're located in such a way that every country has boundary with every other country, which basically means that we can only use each color once. If I color one country in yellow, like I just did, that means that I cannot use yellow anymore. So I'll have to use another color, other colors for other countries, for the rest of the countries. So maybe I'll use green for this one, but after that I cannot use green again. So I'll have to choose yet another color. So basically I'll have to use as many colors as there are countries. So there are 4 countries. I'll need 4 colors. So I do need at least 4 colors for this particular map, and therefore if we want to find the number of colors that works for any map, well, it has to be at least 4. Alright, so the last country here is kind of large, so let me not be so precise with this last one. So let's color it in purple. So it's going to be like that. All right, so yeah, so we need at least 4 colors for this particular map. So so that means that the answer to our question has to be at least 4. So we need at least 4 colors. And then there is a theorem called 4-color theorem that basically says that 4 colors are always enough. However, this is a very hard theorem. And in fact, the proof requires a lot of computer computation. Some huge computer computation. So it is impossible actually to check it by hand. So we're obviously not gonna do that in this course. So instead, we're going to prove some weaker versions of this theorem. But first, before I get into that, I want to discuss the connection to the graph theory, to coloring graphs. So in the previous lecture, we were coloring the vertices of graphs, and this time I'm coloring maps. So that seems to be somewhat different. However, it is actually very closely related. And to explain this relation, one needs to consider dual graphs. So let's look again at this map we colored before, and let's see what a dual graph is. So we start by putting vertices, one in each country, so kind of a capital, if you want, in each country, like that. And then what do? We connect those vertices, but if and only if the corresponding countries share a boundary. So if the corresponding countries are neighboring countries. And moreover, we can do it as we do this, we can draw this graph on the plane, so that we get a planar presentation, so that we can make sure that the graph is planar. So how do we do this? Well, we just take a piece of boundary between two countries, say this piece. We start with this piece, and we connect the corresponding two vertices by crossing this particular piece of the boundary, like that. And kind of, for each country, we just go, say, clockwise here. So I took care of this piece of the boundary. I go to the next piece, this one, and I draw the edge that crosses that piece of the boundary, and so forth. So I have this piece of the boundary over here. I draw the edge across that. Then I look at the next, say, okay, now I'm kind of going counterclockwise around this, the next country, but that doesn't matter. So basically we just need to consider every piece of every boundary like that, and just draw the corresponding edges. So the good thing about going like that, just indicating which piece of the boundary we are going to cross now, is that in that way we can avoid missing edges. So for example, here this piece of boundary kind of stops here, right, and we get this edge, and then the next piece of the boundary here is very short, like that. However, it's still a piece of boundary, and we still need an edge crossing it, like that. Okay, then next we go here. Yes, that's this edge. Oh, I did forget one, right? So I do have a piece of the boundary here, so I have to draw the corresponding edge as well. And I continue. So say this one, and the edge, like that. And then this piece. And, well, just a little bit more. We connect these two vertices, and two final pieces of the boundary. Here, this one, and that one. So that way we get this graph, which is called the dual graph, graph dual to the map we started from. And the important part here is that clearly the proper colorings of the map are just the same thing as proper coloring of the dual graph. So coloring the map, like here, is the same as just coloring the graph, the vertices of this dual graph, because basically the vertices correspond to the countries, and the two vertices are connected if and only if the countries share a boundary. So if we have a proper coloring of the dual graph, we get a proper coloring of the map, and vice versa. One can also show, that's not very hard to do, but I'll skip that, that basically if you have a planar graph, then you can draw a map that corresponds to it as well. So therefore this coloring maps and coloring planar graphs is just the same thing. So now with this in mind, we'll focus on coloring planar graphs rather than maps because it's kind of a little bit more convenient to work with. So the next thing I want to do is to prove the 6-color theorem. So remember that this hard theorem was 4-color theorem, and but 6-color theorem is relatively easy, and that's what we will start with. So the theorem says that every planar graph has a proper 6 coloring, so coloring in 6 colors. So in the proof, the key fact is something we proved last week, that says that every planar graph has at least one vertex of degree less or equal than 5. So that was a theorem from last week. So basically it says that if the planar graph, if a graph has the minimal degree greater than 5, then it cannot be planar because there are too many edges, basically. We had a bound on the number of edges for a planar graph. And if all the degrees are greater than 5, then it cannot happen. Now, what we're going to do, we're going to do induction in the order of the graph. And the base of the induction is very simple. So if the order of the graph is less than 6, or less or equal than 6, then we just and we have 6 colors, so we can just, if we have less or equal than 6 vertices, we can just use one color for each vertex. So we just use one color okay, maybe not like that. How do I say this? Just color all the vertices in distinct colors. Vertices in distinct colors. So basically we don't use the same color twice. We have enough colors to just do color all the vertices in distinct colors. So the base, as you can see, is very straightforward. Now we do need to do the inductive step. So our inductive assumption is that the theorem holds for planar graphs of order less than n, and then we have a graph of order n, planar graph of order n, and we need to color. So how are we going to proceed? Well, we use this fact that there exists a vertex of degree less or equal than 5. Now we remove this vertex from the graph, we get another planar graph. So this G without F is also planar. And also the order of this graph is what? It's n minus 1, which is less than n. So we can use inductive assumption. So which means that we can color it. We can color this G without V with our 6 colors. And now what do? We're gonna put this vertex V back. So we have this vertex V. It has order less or equal than 5. So it has at most 5 neighbors, 5 adjacent vertices, like that. At most, maybe even less. And what that means is that we only used at most 5 colors for on its neighbors. Maybe we might have used the 6th color somewhere far away, but on the adjacent vertices we use at most 5 colors, and which means that we can color our vertex 6 in the 6th color, and that's it. So that means that we can color G like that. So maybe I should write some words here. So we put the vertex V back, and then we observe that there are enough colors to color it properly, since V has at most 5 neighbors. So that's it. So that means that we can color by induction, we can color the whole graph. So basically, if you think about it, the strategy is as follows. We find the vertex of degree less or equal than 5, we remove it, we color it using inductive assumption, and then we put it back. All right. So this is a 6-color theorem, but it turns out that one can improve it and prove the 5-color theorem in a similar way, but with a little bit more work. So let's do that. So in fact, it's enough to have just 5 colors. Well, we know that it is enough to have 4 colors, but that's hard. That's a hard theorem. So what 5 colors is not that hard. So let's see how it's done. So again, we do the induction in the order of the graph. So the base is the same as before. Right? So if we have, if we have less or equal than 5 vertices, we can just color the vertices without using the same color twice, and that's going to be a proper coloring. Now the inductive step. So once again, we assume that the theorem holds for planar graphs of order less than n, and we take a graph of order n. Now our goal is to color it. So this is an arbitrary graph of order n, planar graph of order n, and so yeah, we need to color it. So now once again, we know that there exists a vertex of degree less or equal than 5. So we'll take this vertex. Now the first case is if the degree of V is less than 5. Well, if that's the case, then we can proceed the same way as before, because then 5 colors are enough to color it. Because so what do? So we say that we color G without V by inductive assumption, and we say that and then we put V back, and we have enough colors to color it. So in this first case, we proceed the same way as before. So the interesting case is when we have the degree is equal to 5. Now we do the same thing. We use inductive assumption for G minus V. We color. So if the neighbors of V, if 2 of the neighbors of V are colored in the same color, then we still have enough colors to color V, because in total then we have less than 5 colors used for the neighbors, so we can color V. So otherwise, we have exactly this picture. We have our vertex V. Over here we have 5 neighbors, W1, W2, W3, W4, and W5, and they're all colored in different colors. So let's say that W1 is colored in the first color, W2 in the second, W3 in third, W4 in fourth, and W5 in the 5th color. So now, we have to do something more clever, because right now we cannot really put V back, so we cannot color V in any of the 5 colors. So we have to be smarter about this in some way. So let's see. So here we have to use the following trick. So we consider a connected component. The connected component H, which I will call H, of W1, so containing W1, of the subgraph induced on the vertices colored in color 1 and 3. So in other words, what I mean is that we consider, we kind of remove all the vertices that are colored in colors different from 1 and 3. We only leave the vertices that are colored in 1 and 3. And then we consider the part of this, of the remaining graph that contains W1. W1 is colored in 1, so it is in this subgraph. So basically, we just look at all the vertices of color 1 and 3 that can be, that are kind of attached to W1 through other vertices of color 1 and 3. So maybe we might have a picture like that. So, okay, so there might be several vertices like that. So some of them are attached to W1, which means that they are colored in color 3. Then maybe some other vertices are attached to those vertices, like that, and then those have to be colored in color 1. Maybe there are some other connections like that. Then maybe more vertices attached like that. Then this has to be colored in 1. So, but anyways, we just consider the vertices that are colored in 1 and 3, and we consider the connected component of the resulting graph containing W1. So there might be more vertices here, so of some other colors. So let's say of color 3 attached to those vertices. Oh, not 3. 3 is, sorry, say color 2 attached there, like that, or maybe like that. That's fine, but it is not colored in 1 and 3, so we don't consider it. So this is our subgraph H here. So there are two cases. So this first case is when W3, so note that there is also this vertex W3 colored in color 3. So there are two cases. W3 is outside of H and W3 is inside of H. So let's consider the case when W3 is not in this subgraph. So that means that we cannot get from W1 to W3 by alternating colors 1 and 3, basically. So there is no way to do that. So in this case, what we can do, oh, this is supposed to be a planar graph, and what I've drawn is not planar, so I'm sorry, I should remove this vertex. Maybe let's put it here. So this is 3, and it's attached like that. So it's supposed to be a planar graph, right? It is a planar graph. All right. So now what we can do, we can switch the colors in this subgraph in subgraph H. So we switch one and 3 in H. So basically, all other vertices not in H attached to the vertices of H are not colored in 1 and 3. They are colored in some other colors. So as we switch the colors in H, we are not breaking anything. So the resulting graph is still the resulting coloring is still going to be a proper coloring. So let's do that. So we just replace 1s with 3s and 3s with 1s. So I put, instead of 1, put 3 here, 1 here, 1 here, 3 here, 3 here, and 1 here. And now, so now it's still a proper coloring, and you can see that color number 1 is not used in the neighbors for the neighbors of V. So we can color V in 1 in color number 1. So we just, okay, maybe I should put red there. So colored in 3. And not 3, 1. I'm sorry, I wrote correctly, so 1. So color number 1 is not used for the neighbors anymore, so we can color it in 1. Now the second case is a little bit more interesting. So W1 is now inside of H. So what that basically means is that there is a path from W1 to W3, maybe going something like that. And along this path, we only use colors 1 and 3. So they have to alternate because so we have so yeah, the colors should be, that should be 3, that should be 1, that should be then 3, then 1, 3, 1, yes, and so like that. So in this case, we cannot use the same strategy as before, because if we switch, there might be more vertices, by the way, at, inside H. So there could be some vertices, say here. Let me put it like that. Maybe like that, colored in 1, 3, 3, say 1. And there could be also some other vertices colored in other colors attached to it, but we have this alternating path like that from W1 to W3. So yes, we cannot switch the colors 1 and 3. We can switch the colors 1 and 3 in this subgraph H. Maybe I should kind of circle it. This is our subgraph H this time. However, if we do that, then W1 is going to be colored in third color, and W3 will be colored in the first color. So that's not gonna help. We're still gonna have all the colors used for the neighbors of V. So the idea now is to use consider another subgraph H prime, and this time we take the connected component of W2. W2 is here, and we consider the graph with vertices colored in only second and the fourth color. So the point now is that this path we created from W1 to W3, which is colored in 1 and 3, it separates W2 from W4. And what that means is that we cannot connect W2 to W4 by alternating colors 2 and 4. So in other words, W4 does not belong to H prime. So we have this so H prime, it's not gonna contain, so this is our H prime. By the way, this was our H, and this is our H prime, so it contains it is the connected component of W2 if we consider only colors 2 and 4. So say this should be then 4 and this should be 2. So we can see that this subgraph, it cannot contain W4, and therefore we can flip the colors in this subgraph H prime. So now what do? We just remove these colors and we flip them. So now W2 is going to be colored in 4. Its neighbors, those of its neighbors that are colored in 4 are now colored in 2, and so on. So we flip the colors in this subgraph H prime. And after that, the color number 2 is not used for neighbors of V, so we can color V in this second color, like that. And that's it. That's the end of the proof. So that is the idea. So once again, we try to find a subgraph where we can flip the colors so that one of the neighbors one of the neighbors' color got changed, so that now not all the colors are used for the neighbors. And we can see that we can always do that. So first we try to do it for colors 1 and 3. So, but if we are not successful, then the corresponding path will separate W2 from W4, and therefore we'll be able to do it for this subgraph H prime of colors 2 and 4, and the connected component containing W2. All right, so that's it. That's the end of the proof. So once again, we were able to prove that 5 colors are always enough to properly color any planar graph. However, there is also this fancy hard theorem that actually says that 4 colors are enough, but we didn't prove it today because that is a hard theorem requiring a lot of computer computations, in fact.